So our introducer of the speaker today is our own Dr. Kraus, yes, who is now occupying Dr. This is Dr. Kraus's first year here as a professor, not his first year here at LeTourneau, yes? And he graduated when?
2010.
2010. So he graduated just not so many years ago. And are you the youngest faculty then?
I am the youngest faculty member, yes, but Andrew Davis is almost a faculty member, and he'll be younger than me.
Okay,
Yeah.
so, all right, but, you know, first not a competition there for the youngest. All right, then we got Armstrong over here. So, yep. All right, so we're happy to introduce our introducer, who will introduce our speaker. I got everyone to be around.
All right, well, happy Thursday to you all. It's an honor for me to introduce Elizabeth Lick and her presentation. So I've been asked to give a little bit of background about this presentation and the project. So Elizabeth first approached me last semester and asked to do an honors project in mathematics for a course, Abstract Algebra, that we are taking right now this semester. And so I didn't know Elizabeth at the time, but I had heard really good things about her as a student, and I was very excited to be able to do that with her. And so as we began talking, you know, we found that we had a lot of common interest in this idea of creativity in mathematics and how, you know, if you look at all the really great discoveries and great discoverers of mathematics and the science, they often claim that they were led to their solution by this sense of beauty and this sense of elegance of the solution. And so we were both really interested in that, and, you know, we wanted to sort of discover how creativity and beauty sort of interact with one another, and if that says anything about our common creator. And so we've gotten together every week over this semester on Thursdays, and, you know, just nerded out and talked about how awesome math is, so that's fun. But then we also, you know, are trying to challenge ourselves as well. You know, how do we present these ideas to other people who might not be as enthusiastic about math as we are? So I know she'll do a good job. Here's Elizabeth.
Before I begin, I just want to say thank you to the LeTourneau Science Department and to Dr. Kraus for working with me through this semester and helping me, challenging me to think deeply and differently about how I view math and how that affects my life. So I want to start with a question. Is mathematics creative? And a lot of people would answer this question with an emphatic no. Of course mathematics is not creative. It's all about rules and theorems. But let's pause for a minute and let's consider if, by way of contradiction, mathematics was creative. What would that look like? Could somebody study math not to find application, but simply out of enjoyment? Many mathematicians claim that math is, in fact, a creative endeavor. So does that make it more of a science or more of an art? Most of you in this room are probably engineers, and so you would say that mathematics is a science, that we develop it in order to apply it to problems that we see in the physical world. But mathematics is not only application-based. Much of mathematics, especially in the Greek tradition, was developed because people were curious. They found concepts intriguing and captivating, and so they studied them. And they didn't have applications for this math, and it wasn't until later when scientists had problems that they couldn't solve that they went back to this old math that didn't have applications, and they found that it was the solution to the problem that they were looking at. So to help answer this question, let's examine a few things that we think of when we hear the word science. We think of the scientific method, a specific process for discovering correlations and showing outcomes. We think of empirical evidence, making interpretations and hypotheses based on observable data. We observe the world around us and we draw conclusions about how things work. So science is developed for the purpose of understanding and applying information about the world. And when we think about art, we think of very different things. Art is often said to have intrinsic value, that it has meaning even if it doesn't have a purpose or even if it's not useful. We see art as conveying a message. Maybe this is a message that can be challenging to express through words, and so we use art as a way to express this message. Art usually has a sense of beauty, and yes, we can, as people, we can see, maybe we define beauty differently, but we see that there are certain characteristics which define beauty that are pervasive throughout art. And lastly, art is used as a representation of a specific perspective of the world. Maybe that's somebody's opinion, or maybe that's just them drawing a picture of a natural landscape and representing the world that way. So which of these fits math more than the other? Well, we know that math is based in logic and reason, that we draw conclusions and derive statements based on other statements. And these statements often describe the world around us. They are represented in proofs, and we can draw conclusions based on them. And that sounds a lot like science. But then we can consider how mathematics is not always studied for application, but due to curiosity, patterns, and elegance. There's a sense of beauty in mathematics, and this often represents the world from what we could say is a specific perspective. I like this quote by Bertrand Russell. He's a mathematician, and he said, "In the most beautiful work, a chain of argument is presented in which every link is important on its own account, in which there is an air of ease and lucidity throughout, and the premises achieve more than would have been thought possible by means which appear natural and inevitable." I feel like this statement does a good job of describing how there can be beauty in a mathematical argument, but it also has a scientific aspect, that it's moving towards a purpose. So let's say that mathematics is, as a whole, both a science and an art. So for it to be creative, we have to decide whether math is something which can be created or whether it is something which already exists. And this is a question that many of you might not have considered, but it is actually deeply linked to how we think about mathematics. And there are two main perspectives with respect to this question. Plato advocated for the perspective of realism, and this states that mathematical objects are real, that they truly exist independently of human minds, and that human minds are able to apprehend them. Thus, mathematical knowledge consists of justified, true beliefs about these objects. So realism assumes that mathematics is innate to creation, and that humans can study the mathematical structures that we see in the physical world, and they can learn about them. And the contrasting view is constructivism. And this says that mathematical objects or properties do not exist until they are found or constructed explicitly. From this perspective, mathematical objects do not exist apart from human minds. So the question of whether mathematics is invented or discovered has been a topic of much controversy for a long time. If realism is true, then the pursuit of proving and disproving mathematical statements is actually a pursuit of truth, as humanity aims to understand how creation works. On the other hand, if constructivism is true, then mathematics, although it is creative, has this element that is arbitrary. Humans can construct this mathematical framework and they can describe the world with it, but there's no physical basis to show whether it is absolutely true or not. And so I want to propose that mathematics is made up of a little bit of both. That mathematical structures are innate to creation, and that humans have the creative ability to invent the notation and the way of describing these mathematical structures that we see in the world around us. So consider this statement. Some mathematicians have suggested that the choice of definitions is purely subjective. However, this loses sight of the fact that different civilizations have often studied essentially the same objects independently. And this statement shows us that constructivism cannot be wholly true. Because we see evidence of the same mathematics being studied in different civilizations at different points in history, independently of one another, we're led to see that there is mathematics that is pervasive in our world, and that exists independently of the human mind. So if mathematics is in part, at least, a creative endeavor, then how do mathematicians decide which direction they should go when they study it and when they develop math? We've already established that math is not solely based in application, so there has to be some other driving force, some other motivation for why we study math. And perhaps mathematicians study math because they are drawn to its beauty. But what would that mean for math to be beautiful? The book, Mathematics Through the Eyes of Faith, outlines a list of attributes for beauty which can be seen in mathematics. And these include pleasing to the senses, symmetry, infinity, surprise and paradox, relationships and depth, elegance, harmony, brevity, simplicity, economy, tension and relief, originality, power and fruitfulness, and complexity. And these attributes are everywhere in mathematics, and they point to the beauty of the subject. And what is more, these attributes are not unique to mathematics. We actually see them in beauty as a whole. We have a beautiful painting, and that often contains symmetry. A beautiful piece of music highlights harmony, tension, and relief. And so actually, we can make the argument that not only are these attributes not unique to mathematics, but that mathematics is at the core of what makes other things beautiful. And so I want to go through a few examples of, within mathematics, how we can see some of these attributes and see the beauty in them. So the first one I want to talk about is infinity. And I want to make the claim that there are as many natural numbers as there are even natural numbers. And this statement doesn't really make a lot of sense, because if I was to take all of the natural numbers between 1 and 10, I would have 10 numbers. If I was to take all of the even natural numbers between 1 and 10, I would have 5 numbers. So naturally, we would assume that if I was to take all of the even natural numbers and all of the regular natural numbers, I would have half as many even as I do natural numbers. But this is actually not the case. So if we take the natural numbers, 1, 2, 3, counting on up into infinity, we can define the cardinality, that's the mathematical term for the number of numbers in this set, the quantity. And the cardinality of the natural numbers is said to be infinity. And then if we look at the even natural numbers, 2, 4, 6, 8, 10, continuing on to infinity, the cardinality of the even natural numbers is also infinity. And I realize that infinity isn't something that can be necessarily quantified. But mathematicians have been able to identify that there are different levels of infinity, that some infinities are larger than other infinities. And so we would assume that that would be the case here, but it's actually not. There are actually the same level of infinity for the natural numbers as there are for the even natural numbers. And the way that we know this is if we take the natural numbers, we can map each natural number to a corresponding even natural number. So 1 maps to 2, 2 maps to 4, 3 maps to 6. And because we can know that there is a partner for every even natural number to a natural number, we know that there must be the same amount of them. If we can map each of them to a pair, then we know that there has to be the same number. And I find this really fascinating because it kind of defies what we think about finite sets. And we see that there's kind of a sense of surprise and beauty that comes out of looking at infinity, how it has different properties, how it's something that's intriguing, that we don't understand, and that we can look more into. The second example I want to talk about, I was looking at the list of attributes, and I noticed that simplicity and complexity were both on the list. And I was wondering, how does that work? How can something be simple and complex at the same time? And I realized that when we combine simplicity with complexity, what we get is intricacy. And I immediately thought of a fractal. So the fractal I have here is the Sierpinski triangle. And the simplicity of it is that it's very easy to construct. What you do is you take an equilateral triangle with a solid area, and you divide it into 4 smaller equilateral triangles, and then you remove the middle one, so you create a hole. So now you have 3 small equilateral triangles with a hole in the middle. And then you do the same thing to each of those smaller equilateral triangles. Then you have 9 of them. And you continue this process over and over again as many times as you want. So it's simple in that we're using simple shapes and we're doing a simple operation. But the complexity comes when we look at the area of this fractal. So we started out with an equilateral triangle that had a solid area. And after a certain number of iterations, if we took the area again, it would be a lot smaller because we would have been removing sections from it. And the interesting part is that if we do these iterations out to infinity, we're actually left with a shape that has no area. And that's really interesting to think about. It kind of ties back to the infinity again of what are those interesting properties? How is this intricate, even though it's such a simple design? So another example of surprise or paradox that I want to talk about is with the imaginary number I. And I want to propose that I raised to the power of I is a real number. So we know that I is an imaginary number. It's not a real number. So how can I raised to the I power be a real number? I'm going to work through the proof of this. It's pretty short. And at the beginning, we're going to assume that Euler's formula is true. So Euler's formula says that e to the pi I is equal to cosine of pi plus I sine of pi. And there's a proof for this, but I'm not going to go through it in this presentation, so we're going to assume that this is a true statement. So we can work out the trig. Cosine of pi is -1. Sine of pi is 0, so we're left with e to the pi I equals -1 plus 0I, or just e to the pi I equals -1. And I want to pause because this is actually a very famous equation, and it's considered to be one of the most beautiful mathematical equations. And the reason is because it incorporates e, pi, and I, which are all very profound mathematical concepts, and it combines them in a way that we get a very simple answer, -1. So continuing on with our proof, we're going to raise both sides to the 1/2 power. So we have e to the pi I to the 1/2 and -1 to the 1/2. And we're just going to rewrite this. E to the 1/2 pi I equals square root of -1. I just rewrote the power of 1/2 as a square root sign. And we know that the square root of -1 is equal to I. So now we have e to the 1/2 pi I equals I. So let's raise both sides to the I power. And then we end up with e to the 1/2 pi I squared equals I to the I. And we know that I squared is equal to -1. So now we have e to the -1/2 pi equals I to the I. And e to the -1/2 pi, that's a real number. It's about 2.07. It's about a fifth. And I found that really fascinating, that we can take an imaginary number, raise it to the power of an imaginary number, and get approximately 1/5. That's, blew my mind a little bit. So I have one more example. So I have two rectangles up here. And if you were to state which of these rectangles you thought was the most aesthetically pleasing, the most visually appealing, think about which one you would say. Most people would say the top rectangle, but they wouldn't really be able to articulate why they found it the most aesthetically pleasing. And it has some very interesting mathematical properties that I'm going to talk about a little bit that are related to aesthetic beauty. But before I do that, let's look at this sequence of numbers. So we have a sequence of numbers here where every number is the sum of the two previous numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. This pattern continues. So this is the Fibonacci sequence. And it contains some really interesting mathematical characteristics. We were to take every element in the Fibonacci sequence and divide it by the previous term. We're getting a ratio which approaches approximately 1.618. So I'm taking 1 divided by 1, then 2 divided by 1, 3 divided by 2, and as I continue on, I'm getting with greater and greater accuracy an irrational number which is approximately 1.618. And this ratio is called the golden ratio. And the rectangle that I showed you in the previous slide has this ratio in its proportions. So if the short length of that rectangle was 1, the long side of that rectangle would be 1.618. And this is considered to be the most visually appealing ratio. And we see that the golden ratio, that it appears in art, that it appears in architecture, and this is often without the artist's intention. And so we see the Fibonacci sequence showing up over and over again. In the Parthenon we see it, in the Mona Lisa we see it. We see the golden ratio incorporated into nature, in the nautilus shell, other spiraling objects. And the way that we can construct the golden ratio is if we were to take squares of side length with each Fibonacci number, so we have a square of 1, a square side length 1, and then another square side length 2, we're constructing larger and larger rectangles, and each of those rectangles has proportions approaching the golden ratio. And so it's really interesting that this is not only something that appears naturally in art and architecture, not even intentionally, just because we see it as something that's beautiful, but we also see it in nature, and that's something that's very interesting. So why should we study mathematics? We've talked about it as a combination of science and art, and so I think the reasons why we study mathematics should likewise combine science and art, application and beauty. So on one hand, we should study math because it is applicable, because we have problems in the real world that we need to solve, and mathematics can help us do that. Mathematics allows us to understand creation better, and it gives us clarity on things that are very complicated. But mathematics is also beautiful, and we should study it as an art, with the intention of creating new and lovely situations which may not presently have application. We should study mathematics because it is captivating, and because it's intriguing and enjoyable to think about it deeply. And so my next question is how we as Christians should engage with mathematics. And you may say that mathematics is a purely objective subject, that you can't engage with it from a worldview, Christian or otherwise. But I think that the way that we look at mathematics as Christians is and should be fundamentally different than those who do not profess our faith. So the first claim I would like to make is that we are drawn to mathematics because its elements of beauty reflect characteristics of God. We are drawn to things that are infinite, that have patterns, that are balanced. And these are things which we all see in our Creator. As Christians, we should see math as a testimony not only to God's existence, but to the fact, an example of who He is. So we should study math, and we should see math as beautiful because God is beautiful. We should be able to marvel at the order in which He created the world around us and stand in awe of the one who put so much detail into creation. The study of math, I believe, is a form of worship to God because it praises Him for His intentionality. And if He so intentionally put so much detail into creation, how much more must He love each individual who He created in His image? And so I believe that the pervasiveness of math in our world is evidence of God's great love for us. And the second claim I want to make is that our creation in the image of God instills in us the fundamental desire and ability to create. God designed and created the universe, and He gave us the ability to innovate and think creatively as well. He desires for us to study, to learn. And I think that as we view the study of mathematics, we should see it as a way to learn more about God, but also as a way to live in part of what He designed for us to do. We should have a sense of reverence for creativity, recognizing that it is a gift from God, and seeking to be able to walk in His ways and steward that gift well as we pursue the study of mathematics. And my last claim for how we should engage with mathematics is that it requires an aspect of faith. Mathematics is built on a foundation of axioms. So we prove statements based on others' foundational statements. But at some level, we have to have axioms which we cannot prove. And we have to have faith that those axioms are true in order to build the rest of mathematics on them. And while mathematics may be a subject which contains possibly one of the lowest amounts of speculation because we can prove so many things logically, it still requires an element of faith. And I think as Christians, it's important to realize that that same element of faith which we have in the fundamental axioms is the faith which we must have in God. And we need to realize that when we put our faith, or when we put our trust in those fundamental axioms, what we are really doing is putting our trust in God, that He created those and that He will allow us to study and develop math based on those axioms. So one major implication of how we engage with mathematics is how it is taught. And in order to formulate how we teach mathematics, we must identify what its purpose is. Again, this is something that I believe should incorporate both application and beauty. So, teaching mathematics should include an education in the fundamental patterns and formulas which we see in current mathematical education, but also a development of mathematical intuition and insight. Today, our education system mainly focuses on the formulaic aspect of this, and that is necessary. It is necessary to equip students with the tools needed to go and learn about higher math and to apply these things in the real world. But I think students also need to grow in their ability to think insightfully about mathematics and search for creative solutions. Many students are not exposed to this type of thinking until proofs-based courses in college. But I think the ability to think intuitively about mathematics is critical for the development of new math and also for preserving the sense of awe and wonder at what mathematics truly is. And part of this type of thinking is also important to convincing students that mathematics is not just a set of arbitrary rules that the teachers provide and that we function under. Allowing students to see that mathematics is something which is pervasive shows them that it's credible, that these rules and these formulas which we're using don't just come from a textbook, but they come from years of study by other mathematicians, and more importantly, that they come from something that's innate to creation. And so I think students should engage with math history. This would give them a window into how math was developed, and they would be able to see that creative process. And so in order to uphold the true identity of mathematics, I believe that it is vital that students are allowed to struggle with problems, to think creatively about them, and to think about why mathematics is true. In 2002, Paul Lockhart published an essay entitled The Mathematician's Lament, and he critiqued the current mathematics education system. He compared math education to a painter who woke up one morning having had a nightmare that students in the classroom were not being exposed to true painting and true art, but only allowed to do color theory, painting by number, and work within boxed-in systems. And there's an exclamation that says, "But mostly, we're just trying to give these kids a good foundation in what painting is all about. So when they get out there in the real world and they paint their kitchen, they don't make a total mess of it." And the point that Lockhart here is trying to make is that math education has perfected the teaching of these formulas. And so much so that students no longer understand why they're doing the math. And later in his article, he says that, yes, it is necessary to be able to read, to fill out forms. But that's not why we learn how to read. We learn how to read because it's something that's enjoyable and that's worthwhile. And he makes the same claim here with mathematics, that we do need mathematics to apply to things in the real world. But that shouldn't be why we study mathematics, and that shouldn't be why it's important. And he goes on to say, if I had to design a mechanism for the express purpose of destroying a child's natural curiosity and love of pattern making, I couldn't possibly do as good a job as is currently being done. I simply wouldn't have the imagination to come up with the kind of senseless, soul-crushing ideas that constitute contemporary mathematics education. This is a very extreme statement. But Lockhart brings up some good points. Namely, that children do have a natural curiosity and desire to learn, and that is something that we should nurture, something that we should support and encourage. And he suggests that mathematics should be taught in a way through which students are compelled to discover these mathematical principles on their own, with the guidance of a teacher, but allowed to struggle with these problems. And this type of education would certainly prepare students for proof-based courses and for mathematical research in the future, and it would uphold the identity of mathematics. But there are also holes in this type of teaching. Expecting a child to completely reconstruct the entirety of mathematical foundations with minimal assistance is a little bit insurmountable, especially since this mathematics has been developed over millennia by many people. And so having this task to children in a classroom seems a little bit unrealistic. This type of education is also very time intensive. Mathematics, it should be appreciated, and we should spend time on it. But the understanding of fundamental principles, that must not be sacrificed in order for children to develop this on their own. And I would argue that memorization and formulas, if they are taught and used properly in the classroom, still have their place in mathematics education. For example, the memorization of multiplication tables is something necessary if a student is to go on to higher level math. If a student doesn't easily know that 5 times 6 is 30, they can get really bogged down in arithmetic and make a lot of mistakes. So much so that they may not be able to understand and learn algebra correctly because they're so stuck in the multiplication tables. And so I think that there is a place within mathematics education for memorization and for formulas as well. So I want to propose that students should practice this type of intuitive thinking as part of some sort of a daily math exercise, but that we should still uphold current math curriculum. So before I close, I have a few examples of types of exercises that we can present to students to help them think creatively about problems like this. So the first one I want to look at is a proof of the area of a triangle. So we have a triangle inscribed in a rectangle, and we know the area of the rectangle, but we don't know the area of the triangle, and we're trying to figure it out without the formula. So this is something that you could give to students at a pretty young age, something that they could manipulate. Maybe they could draw on it or move it around. And eventually, with guidance, they would realize that if you drew a line through the vertex of the triangle, it would split the rectangle into 2 smaller sections. And with this line here, it can be easily seen that the area inside the triangle is equal to the area outside the triangle for each of those independent sections. And thus, if the triangle takes up half of the area in each section, it must take up half of the rectangle as a whole. And this is where we get the formula, 1/2 base times height. Base times height being the area of the rectangle, and 1/2 base times height being the area of a triangle. And we see that it is true that it is taking up half of the space of that rectangle. The second proof I want to do is a geometric proof for the Pythagorean theorem. So we're all aware that for a right triangle, a squared plus b squared equals c squared. That's something we know, that's something we've memorized, that we use a lot. But where does it come from? And there are several proofs for the Pythagorean theorem, but the one I want to talk about is a specific one that I think, again, you could present to students and have them see where this comes from. So we'll start with a right triangle, and it has side lengths A, B, and C. We'll take this right triangle, and we'll add 3 more of them. Right triangles. And then there's a space left in between them. And that makes up a smaller square of side length C. So we'll take this larger square and we'll duplicate it. It still has the same properties, side length A plus B. And we'll take the same 4 right triangles and we'll also put them into the second square. But we're going to rearrange them. So we'll put 2 up in the upper corner and 2 in the lower corner. So we still have side length A plus B. We still have the same 4 right triangles within the square. And because we have the same size square with the same amount of space filled up, we know that the space left over in both of these must be the same. So what's left over in the first square? Well, it's a smaller square, side length C, the area of that being C squared. Left over in the second square are 2 squares of side length A and side length B, the area of them respectively being A squared and B squared. And so from that we could see that A squared plus B squared must be equal to C squared. So again, this is something that you could give to students that they could look at and be able to see that A squared plus B squared equals C squared isn't just something, again, that comes from a textbook, that it's something that we can see is true based on a pretty simple proof. So for this theorem, I'm not going to go through the proof of it, but this is something that we could, again, give to students. And Johnson's theorem says that if we have 3 circles of the same size, and they intersect at one central point, then the other 3 points of intersection must lie on a circle of the same size. And we could encourage students to ask questions about this, like what happens if one of the circles is a smaller size? What happens if the circles overlap more or overlap less? What if only 2 of them overlap? And so students could manipulate something like this and be able to come up with this formula based on the characteristics of when it holds true. So they would actually be able to formulate the principles for when this theorem is true based on just observation and trial and error. And my last example is similar, and it says that if you have an equilateral triangle, you can take any point internally and draw perpendiculars to each edge of the triangle, and the sum of those lengths is equal to the height of the triangle. This isn't something that I found to be obvious, so you can't really tell it visually looking at the triangle. And again, students could ask questions about this. What happens if I move the point inside the triangle? And they would be able to see that anywhere within the triangle works. And then they could ask questions like, what if I don't draw the lines perpendicular to the sides of the triangle? And they would see that it fails in that case. Also, we could look at it if it wasn't an equilateral triangle. And again, we would see that it doesn't work. And so I think students are capable of constructing theorems like these through trial and error, through looking at these problems visually. And it's something that I think would be interesting to incorporate into mathematics education. So, in conclusion, I think it's very important that we are intentional in the way that we think about mathematics, that we preserve the sense of awe and creativity within mathematics, that we realize that it is something which is creative, and that we are intentional about, in education, supporting that type of ingenuity and giving our students the tools they need to be able to think creatively about mathematical problems. As Christians, we need to be testing ourselves to see if how we are engaging with mathematics is evidenced with our faith. Are we engaging with mathematics differently than those who do not profess our faith? And how does that affect how we're viewing mathematics as a whole? And most importantly, I think we need to allow ourselves to see the beauty in mathematics, to realize that math is something which is beautiful, to be able to step away from the application and to look at problems and see them as beautiful, and see them as something which we can appreciate, which we can enjoy, and something that is worth pursuing not only just for application. Thank you so much.
Well, I think we have some time for questions for our speaker today. Anyone want to question how mathematics is taught here at LeTourneau? Calc 1 and Calc 2?
So much material.
Yeah, that's a good question, Elizabeth. You know, all of us as professors like this idea of inquiry learning and guided inquiry learning, but it takes more time.
Yes.
And, you know, there's a set of topics that we all have to get through, and it's so much faster just to tell them the way things are. Right? How do you address that issue?
Right. Yeah, that's something that Dr. Krause and I talked a lot about because it is very time intensive. And I think kind of what I had been thinking about was incorporating that maybe as type of an exercise at the beginning of a class on a daily basis type of thing to where students are at least exposed to this type of thinking, although they're maybe not having to develop all of mathematics foundations based on this type of thinking.
So some hybrid type approach. Okay.
Yeah.
Bonus questions.
Dr. Bowman.
In your study of mathematics, or the history of mathematics, what culture has been the most conducive to creative mathematical thinking, in your opinion?
I don't know about the most conducive. I know within the Greek studied math a lot for the beauty of it, and they did apply it, but most of the innovations that they came up with were because they were interested in it, and they were interested in seeing how things worked and why things worked, just because they wanted to see how it was beautiful and how it was created.
Math history is offered in the fall.
Do you see any corollaries between the way in which mathematicians relate to math and the way in which the human writers of the Bible ended up writing their content?
Like, do we see evidence of
Like,
mathematics?
would you say, so, yes, would you say that, like, in the question of do we discover versus do we invent math, would you see any corollaries in this, in the way in which human mathematicians relate with math and the way in which the human writers of the Bible who were inspired wrote the content that wasn't really from them, but it was through their lens, it was through their language?
Right, so like being able to represent something that is already innate to creation and the world around us type of thing.
I was just curious as to.
Yeah, I think that is a sense of that we see that mathematics is something which God has instilled in nature, and that we have the ability to learn about it, and also we can creatively come up with the notation and the way to express that. And I think that's kind of a similar way, within the Bible of having these truths that God has put into creation and humanity, and then being able to express them in Scripture. Yeah.
Do you feel like the shift in earlier education towards what they call the new math, do you see that as a positive shift, kind of doing this exploratory learning, or what's your opinion on that in relation to this
Common
topic?
Core type of mathematics?
I think so. Is that what they're calling?
There's several different movements.
Oh, well,
I
I may be asking a question I don't know all about, but I know there's a shift in how math is being taught on early
Right.
levels.
Common
I
Core again.
Yeah,
think
I guess Common Core.
that is the goal of that type of mathematics. I think it'll take time for it to develop into a way that might be the most constructive to kind of melding that application with the creativity part of it. But I think that people, especially people who are writing curriculum, are starting to realize that the mathematics that we have currently is very application and formula based, and that's not always the best way to teach mathematics.
And that's something actually that Elizabeth and I would like to look at more later as well, that we've only just sort of scratched the surface of, what are some of the sort of philosophical motivations behind Common Core and these other things. And so yeah, it'd be fun to investigate that more.
Do you have any ideas of how technology could help educate children or us as students through like creative means?
Yeah, well, I know that definitely one thing that, this is, I guess, more of a specific thing, but one thing that I have found useful in learning to think about mathematics has been using the ability to graph like three-dimensional objects on the computer and be able to see those and manipulate those in ways on the computer which we can't on a whiteboard and on a two-dimensional surface. And so I think, yeah, technology can give us a lot of ways to be able to look at math differently and see how things relate to each other in more ways than we have in the past.
One possibility is maybe we could have videos of the more creative proofs, even for the ones that aren't actually shown in class, which then people would be given links to, which they could choose to watch those creative proofs.
Your math textbook that you have right now, Jonathan, has those links.
Way ahead of you.
Sorry. Wait, I mean, you guys are busy, right?
Here, I'm talking about like when it comes to like lower grade material, like in high school. Do you think that's a feasible solution there?
Yes.
Because I can see that.
It's a great idea.
So in the past, mathematicians have also been philosophers. How do you see the fall away from mathematicians being philosophers currently relating to this idea of math and intuition?
Yeah, I think we see that in the fact that we aren't currently, at least in the education system, thinking as much about what it means to engage with mathematics in a way that is outside of just this objective thinking. And I think, yeah, the fact that we do view mathematics mainly as an objective subject shows that we've kind of fallen away from the philosophy of it. And in order to get back into that type of perspective, I think the questions that we need to be asking are how we engage as Christians, how we teach math, and how we see math and things outside of just within the classroom. Yeah.
So I was a little bit confused when we were looking at the realism versus constructivism ideas, because at least by the definitions, it seemed like they were entirely mutually exclusive. But it seems as though you're saying that humans, they invent the notation, but that mathematical objects, to use the term you use, exist separately from the human experience. Could you go into what you mean by a mathematical object?
Yeah, so the argument that I'm trying to make is that there are mathematical objects or structures which are innate to creation whether we realize them or not. That mathematics is something which governs how the world, the physical world works, even if we're not realizing it. And so the difference that this distinguishing factor that I was making was, are humans the ones who are creating mathematics and then using it to describe the world, versus the argument that I'm making is that mathematics is something which already exists, that God has put in place into our world, and then we are able to come up with the ways to describe those characteristics which we see them in the world around us, and then we're able to describe them using the mathematics that we develop. Does that make a little bit more sense?
I would say so.
Okay.
Yeah, an example of that is group theory. You know, mathematicians come up with all these constructs of ideas, and then it's the scientists who actually find things that actually relate to those constructs later on. So it's always fun because no matter what problem you come up with in science, there's already a solution in math. They just didn't realize that it was for anything real. It was just a construct to them. So constructs in math become real through the scientists. My opinion. Maybe.
Thank you, Dr. Ford. That's a wonderful way of putting it.
Okay. All right, final question here before we close up.
As a curiosity, how close do TV screens come to the golden ratio?
I don't know, but I have, so since I learned about the golden ratio, I've started looking at rectangles, and you often see them that are rectangles that are very close to it, and I haven't measured them, but just that.
Is that the way? Is that why they put them that way? You know.
I think we see it as something, that
It does.
is visually appealing, and so it's something that we assume would be the most, aesthetically pleasing rectangle to have for, TV screens or different things like
I
that.
actually pulled out my calculator when you did that. The old 4.3 is about 1.333.
It is.
The new one is about 1.87 or something like that. So they're not real close.
And 3x5 cards are, 3 and 5 are both Fibonacci numbers, which means that they are involved in that process of moving towards the golden ratio, so they're pretty close.
So if you want to continue this conversation over lunch, we'll be meeting in the Joyce Room, and Dr. Kraus will be taking on that discussion for Elizabeth, who needs to go to class, I believe. All right, so let's thank Elizabeth one more time.